The waves that come onto the beach here in La Jolla may have come from very distant storms.
In the ocean, a storm has much the same effect as a handful of pebbles tossed into the pond. When you see waves like that crashing on the shore, you quickly realize what tremendous energy they carry. In this program, we're going to look at how that energy is carried across the ocean, and to do that, we need to know how real ocean waves can be measured. We'll begin with a simple situation of waves in a laboratory tank. To remind you of the basic characteristics of waves we've read about in the use of water waves can be characterized by wave length, the horizontal distance from crest to crest, and by height, which is twice the amplitude. They're also characterized by periods, time required for two crests to pass a point, or by frequency, which is the number of crests passing a point at a given time, usually 1 second. In waves, the water particles move in nearly circular orbits. At the surface, those orbits have a diameter equal to the height of the wave. And you remember that there's little net flow of water in the direction of the wave. Beneath the surface, the orbits of the water particles become smaller. As this wax ball slowly sinks, it shows how the orbits change. They become progressively smaller, so that the effect of the wave becomes very small in the depth, which is 1/2 of the wavelength. On the lunar surface, we can hardly aware of heavy waves on the surface. Well, where does wave energy come into all this? From your own experience, you know that large waves carry more energy than small ones. And I expect you remember from the unit, the relationship between wave height and energy is not a simple linear one. Energy is proportional to the square of the height. So by measuring the height of a wave, we can find out its energy. Well, that's fine in theory, but what about a situation like this? So many different waves are superimposed on each other, apparently total confusion. But there's no obvious way height to measure. Well, to begin to analyze this sort of situation, we need to go back to basics and to consider just two simple wavelengths and what happens when they are combined. These two simple traveling waves have got nearly the same frequency. Now let's see what happens when we add them together. Well, you probably realize what's happening here. This is the formation of wave groups, and you should remember how individual waves separate in wave groups. What's the bright wave? It shows how each wave advances through the group and dies out at the front. Now let's look at that again, and that is that individual waves must travel faster than the group. And in real water waves, exactly the same thing happens. And here the group speed is half of the individual wave speed. And for the propagation of wave energy, the group speed is equal, because that's the speed at which energy is carried by waves in water. Just look at this again. Which height would you choose to calculate the energy? Well, of course, you don't do it that way. We know that in this simple situation, these wave groups are made up of only two waves. So if we measured the height and the frequency of the waves in these groups, we could mathematically resolve them back into those two waves that we started with, and that's how we find the energy of the wave group. In the sea, the situation is more complicated, but it's just the same in principle. Wave heights measured over a period of time can be analyzed into simple waves that make up those real wave groups. And once you've analyzed all the heights and frequencies, you can then calculate the energy per frequency and plot an energy density spectrum that looks like this. Realize what it is that's being plotted. You've got energy over frequency plotted against frequency. And so the area under the curve represents total energy carried by the wave. So here's how we can represent the energy of the sea surface after analyzing the real wave group into their components. Well, now we need to recall another feature of waves in water. Different frequencies travel at different speeds. So let's do a little more revision. The speed and length of these water waves is determined by their frequency. Low frequency or long wavelength waves are faster. These sort of increase time. High frequency or short wavelength waves are slower. These take 10 seconds to cover the same distance. Their travel is half the speed of the long wave. And you probably realize what this is. You're looking at an example of dispersion. Waves of all shapes and sizes are generated. They'll spread out confusedly in all directions at once. As they leave the disturbance, the waves begin to sort themselves out. The long waves move out fast, and the short waves more slowly. Away from the disturbance, the confused surface is settled down. The waves are separated and regular, like swelling the ocean. In the ocean, a storm has much the same effect as a handful of pebbles tossed into the pond. In the ocean, a storm has much the same effect as a handful of pebbles tossed into the pond.
The waves that come onto the beach here in La Jolla may have come from very distant storms.